Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome to the deep dive. Today we're looking at the 2025 Nobel Prize in Chemistry. Went to Susumu Kitagawa, Richard Robson, and Omar Yaghi. And really, our mission here is to unpack what they actually did. Because it sounds like science fiction, creating materials based on designing, well, the empty space inside matter. I mean, get this. They figured out how to build stuff where a single gram, like a sugar cube's worth, has the internal surface area of a football field. How is that even possible? And what does that kind of control, that sort of molecular architecture really mean?
It is staggering, isn't it? And that level of control, that architectural idea, is exactly why they got the prize. They invented metal organic frameworks, or MOFs. Think of them as highly ordered crystals, but they're like microscopic sponges. They're built from metal atoms or nodes connected by these rigid organic molecules, the linkers. What you get is this repeating scaffold structure, perfectly arranged, but it's mostly empty space inside, full of tiny, tiny rooms.
The microscopic rooms.
Exactly. And the prize wasn't just for discovering a new material. It recognized the birth of a whole new approach, a field Yaghi actually named reticular chemistry. It's a shift, from just finding what nature gives us to actually designing materials from the molecule up, building them precisely to solve really big problems: pollution, energy, water scarcity.
Designing from the molecule up. Okay, reticular chemistry. Let's break that down. You mentioned a molecular construction set. What are the basic pieces? How do they click together to make all that empty space?
Yeah, the concept is surprisingly straightforward, even if the structures get complex. You basically need just two types of components. Think of them like advanced molecular Legos. First, you've got the metal nodes. These are the joints, the hubs, often single metal ions, sometimes small clusters of them. They really dictate the geometry, the angles and directions of the connection.
Like the corners of a structure.
Precisely. And second, you have the organic linkers. These are the struts, the beams connecting the nodes. They're usually rigid, carbon-based molecules. You mix the right nodes and linkers together in a solution under the right conditions, and they just spontaneously assemble. Self-assembly.
They build themselves.
They build themselves into this huge, perfectly ordered, three-dimensional crystal lattice. And because the linkers hold the nodes apart, most of the structure is just empty space, these pores or rooms. By choosing your node geometry and your linker length very carefully, you can precisely control the size and shape of those microscopic rooms inside.
Right. Let's go back to that scale, though, the football field thing. How do trillions of tiny rooms inside 1 gram add up to 7,000 square meters?
Okay, yeah, it comes down to the sheer number of pores and how incredibly small they are. The Nobel Committee had a great analogy: Hermione's handbag from Harry Potter. Tiny on the outside, vast inside.
Ah, okay. I like that.
Think about a normal sugar cube. Its surface area is just the outside faces, right? 6 sides. Now, imagine that MOF sugar cube. It's not solid. It's this intricate network of interconnected hollow rooms. The total surface area isn't just the outside. It's the area of all the walls inside every single one of those trillions of tiny rooms.
Okay. All the internal walls.
Exactly. Because there are so many pores and their walls are, molecularly thin, the cumulative internal surface area becomes enormous, over 7,000 square meters in just 1 gram for some MOFs. And all that surface area provides countless docking sites for molecules, usually gases. It allows for adsorption.
Adsorption, not absorption.
Right, adsorption. That's key. Molecules stick to the surface like Velcro, rather than soaking into the material like water in a sponge. This makes the process reversible, often with just small changes in pressure or temperature, which is vital for applications like capture and release.
Got it. So the history behind this sounds really interesting. You said it wasn't just one aha moment, but more like a relay race over decades, each scientist solving a piece of the puzzle.
That's a perfect way to describe it. It started, conceptually at least, with Richard Robson in the late 1980s. He was really the pioneer. He was the first to really think about rationally combining metal ions, he used copper, with specific organic linkers to deliberately create these extended scaffolding-like structures. Coordination polymers, he called them. He showed you could design empty space into a material.
But I read his initial structures weren't very robust. They'd collapse if you tried to empty out the pores. Sounds more like a cool chemistry trick than a useful material at that stage.
That was the problem, yes. They were often unstable. You'd make them with solvent molecules inside the pores, and when you removed the solvent, the whole framework could just collapse.
Yeah.
So the porosity wasn't permanent or accessible.
So how long until someone cracked that? Was it Kitagawa? How big a jump was that?
It was a huge leap, and yes, that was Susumu Kitagawa in the 1990s. He directly tackled that stability problem. He developed materials, he called them porous coordination polymers, or PCPs, slightly different name, same idea that didn't collapse. He demonstrated they could absorb gases like methane or nitrogen and then release them reversibly while the framework stayed intact. That was the proof of permanent, usable porosity.
Okay, so now they're stable and porous.
Exactly. And Kitagawa also introduced another really clever idea: soft or flexible frameworks. These could actually change their pore shape slightly, almost like they were breathing, to selectively grab certain gas molecules while letting others pass. Very sophisticated.
Wow. Okay, so Robson laid the groundwork. Kitagawa made them stable and functional. Where does Omar Yaghi fit in? Master architect.
Right. Yaghi really took it to the next level, systematizing the whole approach and coining the term reticular chemistry. Starting in the late 90s, he focused on making MOFs that were exceptionally stable, using really strong chemical bonds, often involving metal ions bonding strongly to carboxylate groups on the linkers. His synthesis of MOF5 back in 1999 became sort of the poster child for the field, a really robust high surface area material. But maybe more importantly, he established the concept of secondary building units, or SBUs.
SBUs.
Yeah, think of it like this. Instead of just mixing individual metal ions and linkers, you think about preforming slightly larger rigid structural units, the SBU, that act as predictable building blocks. The metal node cluster is an SBU, the linker is an SBU. Because their geometry and connectivity are fixed, you can use them like guaranteed architectural components. It allows you to actually blueprint the final giant structure with high confidence before you even start the synthesis in the lab. It made the design truly predictive.
Blueprinting molecules.
Right.
Okay, so Yaghi gives us the reliable blueprints. Where are these things actually being built and used now in 2025? Let's talk about the real-world impact, maybe starting with climate change.
Absolutely. Carbon capture is a huge one. MOFs are basically tunable filters for CoRo because you can design the pore size and the chemical environment inside the pores so precisely, you can make an MOF that loves to grab CoRo's molecules but pretty much ignores nitrogen or oxygen and flue gas.
And how well do they work compared to current tech?
Extremely well in some cases. There's a material called MgMOF74, for instance. Its co-euro uptake can reach about 8.1 millimoles per gram. Now, the current industrial standard is often something called zeolite 13X, which typically manages maybe 4.7 to 6.9 millimoles. So it's a significant improvement in capacity.
Okay, better capacity. What about the energy cost? Isn't that a big deal for carbon capture?
It's critical, and that's another potential advantage. Some advanced MOFs can release the captured co-euro with a much smaller temperature change, a smaller temperature swing, compared to traditional methods. That translates directly to potentially massive energy savings for the whole carbon capture cycle.
Right, that makes sense.
Yeah.
Okay, beyond co-euro, what about cleaning up other nasty stuff, like those forever chemicals in water?
Yes, PFAS removal. This is incredibly promising. These compounds are notoriously hard to get rid of, but researchers have designed a specific zirconium-based MOF, UIO66NCH, technical name.
Catchy.
Ha ha, yeah. But this thing can pull over 99% of PFOA, a common PFAS chemical, out of contaminated water, and get this in less than 5 minutes.
99% in 5 minutes, that's fast.
It's very fast. And there's a cool feature. This particular MOF acts as its own sensor. It actually glows, it fluoresces when it successfully captures the PFAS molecules, so you get instant confirmation it's working.
It glows. That's brilliant. But hang on, if it's that good, why isn't it in my water filter already?
Yeah.
What's the holdup for commercial use?
Ugh. The $1 million question. Or maybe $1 billion. We'll definitely circle back to the challenges, the hurdles like cost and scale. They're significant.
Okay, fair enough. But first, you mentioned water from air, like literally pulling H2O out of the atmosphere.
Yes, atmospheric water harvesting. Some MOFs are exceptionally good at absorbing water molecules even from very dry air. Devices using materials like MOF 801 have shown they can produce up to 2.8 liters of pure drinkable water per kilogram of MOS per day.
Even in the desert.
Even in desert-like conditions, say down to 20% relative humidity. For arid regions or disaster relief scenarios where water infrastructure is gone, this could be revolutionary, truly life-changing technology.
Incredible. Okay, let's shift gears again. Energy. Hydrogen is touted as a clean fuel, but storing it is tricky. How do MOFs help there?
Hydrogen storage is a classic MOF application target. Hydrogen gas is very light, so storing enough of it for, say, a car means either very high pressures or extremely low cryogenic temperatures. Both are problematic. MOFs offer a different solution. They can absorb hydrogen molecules onto their huge internal surfaces, essentially packing the hydrogen densely within the pores, but at much lower, safer pressures.
So more hydrogen in the tank, less risk.
Exactly. For example, a material called MOF 808HH hits 7.5% hydrogen storage by weight at a pressure of just 100 bar. That's actually better than the target set by the U.S. Department of Energy for 2025, which was 5.5 weight percent. It makes hydrogen fuel tanks lighter, safer, and potentially cheaper for vehicles.
So we've got environment, water, energy, but the ability to engineer these things down at the nanoscale must open up other doors. Medicine, maybe?
Definitely. Nanoscale MOFs, or NMOFs, are a really active area. Two key medical applications are emerging. First, targeted drug delivery. You can build NMOFs from biocompatible metals like iron or zirconium, load them up with chemotherapy drugs, and then design them chemically so they stay intact in the bloodstream.
But break down only when they reach the specific conditions around a tumor.
Precisely. Tumors often have a slightly more acidic microenvironment. You can engineer the NMOF to dissolve and release its drug payload primarily in that acidic environment. This targets the cancer cells directly and could significantly reduce the harsh side effects of conventional chemotherapy.
That would be huge.
And the second medical use. Better medical imaging, specifically MRI contrast agents. Right now, agents often use gadolinium ions. By building NMOFs using paramagnetic metal ions like gadolinium, you can pack a much higher concentration of the active agent into each tiny nanoparticle. This could lead to needing lower doses for the patient while potentially getting much clearer, sharper MRI images.
Okay, that makes sense. You mentioned earlier this isn't just about earthbound problems. Space. How do MOFs fit into space exploration?
Right, this is where it gets really visionary. Think about long space missions, like to Mars. Astronauts need breathable air. Current systems on the ISS, for example, use materials like zeolites to scrub co-euro and humidity from the cabin air. But these systems are often heavy and bulky.
And weight is everything in spaceflight.
Weight and volume are critical. NASA is actively researching MOFs as replacement because they can potentially do the same job, removing co-euros and water much more efficiently, meaning lighter, smaller life support systems. But the truly transformative idea is in situ resource utilization, or ISRU, using resources found on site.
Building what you need where you need it, like on Mars.
Exactly. The Martian atmosphere is about 95% MORO. The Martian soil, the regolith, is rich in metals like iron, aluminum, magnesium. The dream is to land on Mars, extract those metals, use the atmospheric co-euro perhaps to synthesize organic linkers, and then manufacture MOFs right there on Mars.
Martian-made MOFs.
To build the essential life support systems, maybe even habitats or fuel production systems for a permanent settlement. It turns the environment itself into a chemical factory.
Wow. That is a truly sci-fi vision built on this chemistry.
Yeah.
Okay, let's bring it back down to earth for a moment. You mentioned hurdles earlier. What are the big obstacles stopping MOFs from being everywhere right now?
It really boils down to scale and economics mostly. Three big things. First, scaling up production. Making a few grams in a lab using precise, often high-pressure, high-temperature solvothermal methods is one thing. Producing thousands of tons consistently and cheaply for industrial use, that's a whole different ballgame. We need continuous flow processes, not just batches.
Lab versus factory.
Second is cost. Performance is great, but they have to compete with existing materials that are often very cheap. Zeolites, activated carbon. These can cost less than, say, $5 per kilogram because they're produced on a massive scale. MOFs, especially those with complex organic linkers, can be much more expensive right now. Economic models suggest they probably need to get down into the $10 to $15 per kilogram range, maybe even lower for some applications, to really penetrate the market. The linker synthesis is often the cost bottleneck.
$10 to $15 a kilo.
Yeah.
Still pricier than incumbents. And the third hurdle.
Durability. Real-world industrial processes are harsh. Materials get exposed to moisture, acidic gases like sulfur oxides or nitrogen oxides, high pressures, constant cycling between absorption and desorption. Some highly effective MOFs, like that MG MOF74 we mentioned for Q arrows, are unfortunately known to be sensitive to water vapor, which can degrade their structure over time. So they need to be stable and robust enough to last for thousands of cycles in these tough conditions to compete with the tried and tested workhorses. That long-term stability is a major research focus.
Okay, scale, cost, durability. Seems like big challenges. But given the sheer number of possible MOFs, You could combine almost any metal, with countless linkers exploring all that must be impossible by hand. Is this where AI comes in?
Absolutely. The design space is just astronomically huge. Millions, maybe billions, of potential MOF structures. Humans can't possibly synthesize and test even a tiny fraction of them. It's a perfect problem for machine learning and AI.
So AI helps sort through the possibilities.
It's more than just sorting now. The really exciting shift is from computational screening, where you'd simulate known or hypothetical MOFs to see what they do to inverse design.
Inverse design.
Yeah, instead of asking, okay, I have this MOF structure, what are its properties? The AI approach flips it. You ask, I need a MOF with these specific properties, say, this exact pore size, this level of co-affinity, stable in water, what is the best structure? What metal, what linker, what topology will give me that?
The AI designs the MOF for the job.
Exactly. There are AI systems being developed, like one called ChatMOF, that use generative models. You tell it the desired properties, and it predicts promising combinations of metals, linkers, and framework structures to synthesize. It can potentially compress years of lab experimentation into, well, minutes of computation. It's massively accelerating the discovery process.
Feels like we've come full circle then. From Robson's first glimpse of designed empty space, through Kitagawa making it work, to Yaghi giving us the architectural rules, and now AI helping us build anything we can imagine.
That really sums it up. This Nobel Prize, this whole field of reticular chemistry, it marks that fundamental shift. From the chemistry of just discovery to the chemistry of deliberate design. Kitagawa, Robson, and Yaghi gave us the toolkit. They showed us how to engineer the behavior of molecules by precisely controlling the voids, the empty spaces they encounter.
A toolkit for building with empty space.
Precisely. And it's a toolkit with this incredible dual promise, isn't it? On one hand, MOFs are tools to help sustain our planet, cleaner air, cleaner water, fighting climate change. On the other, they're these lightweight, high-performance materials that could literally enable us to build new worlds out in space. It's the architecture of the invisible finally made visible through its function.
So for everyone listening, the takeaway seems clear. We're entering an era where we can design materials atom by atom to solve problems that seemed impossible just a short while ago. And maybe the provocative thought to leave you with is this. If that level of control is becoming reality, what fundamental limits does that remove from material science? And looking around you, what everyday item, maybe your car's air filter, your tap water purifier, maybe even your medicine cabinet, what will be the first thing in your life to contain one of these remarkable MOS?
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.